Okay, now we can start. Now let us welcome our first speaker this morning. This is Ron Spiegler from Tel Aviv University, who will talk about cheating with recursive models. Ron, the stage is yours, 45 minutes, 44 actually.
Hey, thank you very much, and thank you for having me on the program. I don't have co-authors, so my co-authors are Kfir Eliaz and Yair Weiss, who's a computer scientist at the Hebrew University. They're not with me here, so they won't help me taking answers. I'll stop for clarifying questions after the introduction and after I present them. Okay, so to motivate the model, I want you to think about the following situation. So you have an analyst or researcher, and for whatever reason he wants to persuade some audience. Don't think of the audience as a bunch of very sharp econometricians. Think about lay people. So he wants to persuade that audience that there's a strong correlation between two variables, x and y. And I'm deliberately putting aside the question of the intended meaning of this correlation. Is it causal? Is it diagnostic? Let's put this aside. So he just wants to persuade people that there's a strong correlation between those two variables. Unfortunately, he can't cheat in terms of data. He can't fudge the data. So the only tool that he has at his disposal is opportunistic choice of a model. So what he does is that he has data, and he's estimating the model, some model, against that data. And he's free to choose that model within a certain class. So that's the instrument that he can use in order to cheat. So that hence the title, Cheating with Models. Now, why would he use models to begin with? Well, of course, we're economists, so we use models all the time. But of course, I could go into a lengthy discussion of various motivations for why you would expect the analyst to rely on models in order to predict correlations. But one reason could be that there is no available data, direct data about the correlation between x and y. However, there is available data about how those two variables are correlated with other variables. And in order to extrapolate the predicted correlation between x and y, you need to make some assumptions, essentially assume a model. So that would be one reason, but not the only one, for using models to estimate correlations. And the question is, that's the question basically, how badly can the analyst distort the true correlation? In other words, how badly can you distort, how much can you cheat about correlations with a misspecified model? A few real-life situations that we have in mind, for example, a pharmaceutical researcher is trying to demonstrate the long-term health benefits of a drug. And for example, it could be hard to come by data about the long-term benefits of the drug, so you need to use something like a surrogate marker, or you may want to argue that you could use something like a surrogate marker. Imagine a scientist who once upon a time claimed that X is a good predictor of Y. Now he has a reputation to defend, so he has a vested interest in showing that X really is a good predictor of Y. However, I don't want you to take this researcher story too seriously, and in fact, that's not how we got to this project. We came to this project with other motivations that had nothing to do with researchers, bad researchers. For example, we're interested in the literature on decision-making when the decision-maker has a misspecified model and uses misspecified models to form beliefs. And the natural question is, problem is to do worst-case analysis of such a decision-maker. So how badly could he err? Therefore, how badly could his beliefs deviate from the truth? So it's basically, you can think of the exercise that we're doing here today as having nothing to do with bad researchers, but just trying to do worst-case analysis of decision-making under a misspecified model. Kfir and I got to this project from a different kind of direction, which is more related to political economics, where the story is that politicians spin false narratives in order to get people on board with their policies. But nevertheless, I will stick to the researcher story throughout the talk just to keep focus. It'll be easier just to have a single story. Now, of course, I need to put some discipline on this class of models that the researcher has at his disposal. And we're going to look at models that take the form of a recursive system of linear regression equations. That's a familiar special case of a very familiar class of models from our introductory econometrics classes. Simultaneous equation models, except it's simultaneous equations without simultaneity, without feedback effects. You have a unidirectional flow of influence from the top of the system of equations to the bottom. So more precisely, the system is recursive if when you have an explanatory variable in one equation, that variable will not appear as a dependent variable in some other equation down the list. And because of this unidirectional flow of influence, it invites causal interpretation. So it's very natural to interpret such a model as a causal model. We're going to put an upper bound on the model's complexity, measured by the number of variables. Therefore, our question will be, how badly can such a model distort the correlation between two variables given a certain bound on the model's complexity? That will be one parameter of the model. So let's go back to our analyst. And before I present the general model, I want to illustrate the basic idea with a very simple example. So now, in this case, suppose that the analyst estimates the following model. It's a recursive model with 3 variables. And he's interested in the correlation between x1 and x3, which you can think of as x1 is the dose of a drug, and x3 is some health indicator. And x2 could be some marker, some surrogate marker. And he estimates the following model. It has 3 equations. The first equation is degenerate, so it's essentially a 2-equation model where you regress x2 on x1, and then you regress x3 on x2. And normalize all the variables so that they have 0 mean and unit variance. Essentially, the identifying assumption of the model is that the analyst assumes that those epsilons are uncorrelated with each other and with the preceding x's. Think of the epsilon as being assumed to be independent. It's a stronger assumption. But that's the analyst. It's not us who make that assumption. The analyst makes that assumption. And if the assumption is wrong, then he has a misspecified model. Okay? Now, and the data that he has is essentially the only thing that matters is basically a correlation matrix. So it's an empirical correlation matrix. And so that's the data, the empirical correlation between pairs of variables. And for example, the empirical correlation between 1 and 3 may be unavailable. And so it's out there somewhere, but the analyst doesn't seem to have data about that particular correlation. So when the analyst has this pair of equations, this equation, the one that regresses x2 and x1, essentially records the empirical correlation between x1 and x2. And the third equation, the one that regresses x3 on x2, records the empirical correlation between x2 and x3. Those are empirical correlation, nothing distorted here. The distortion arises when the analyst extrapolates from these 2 empirical correlations and predicts the following correlation. Based on the model's assumptions, the predicted correlation between x1 and x3 is the simple product of those 2 correlations. So that's the predicted correlation between x1 and x3, given the model's assumptions. Now, suppose that in reality, 1 and 3 are not correlated. So if the analyst didn't cheat, then he should be getting 0. However, it's easy to see, and that's trivial observation, that if x2 happens to be correlated with x1 as well as correlated with x2, then we would have a product of 2 non-zero numbers, and therefore we would get a predicted non-zero correlation between 1 and 3. So we're cheating about that. That's a trivial observation. More interesting observation is that there's a limit to the extent to which this you can cheat that way. The intuition is that because 1 and 3 are objectively uncorrelated, if x2 happens to be highly correlated with 1, such that this is a big number, then this would have to be a small number. So there's a trade-off between enhancing the correlation between 1 and 2 and enhancing the correlation between 2 and 3. So if you imagine that the analyst could choose x2 from some pool of candidate markers, you would face this trade-off. And we could make this trade-off precise. The analyst, effectively, what he does is try to maximize the predicted correlation because he's trying to exaggerate the correlation between 1 and 2. So he's trying to maximize that, subject to the constraint that this matrix is a correlation matrix. In other words, it's positive semi-definite. The ones here on the diagonal are simply because it's a correlation matrix. So you must have ones on the diagonal. And those zeros are the real empirical correlation between 1 and 3. So the 2 instruments, 2 degrees of freedom, are row 1, 2 and row 2, 3. But the constraint is that this matrix is positive semi-definite. Given all these 1s and 0s, this boils down to this inequality. So it's a very simple maximization. Constraint maximization problem. Sorry?
I may be the only one who doesn't know any econometrics. So, but the question is, what's the freedom of choice, strategic choice of the this guy? He can pick beta 1, beta 2. What else can he do?
The beta is given by, he's basically estimating it. He's estimating it via OLS. And again, the way I presented this, it's like he's basically recording. Imagine that he's recording the correlation between 1 and 2 and recording the correlation between 2 and 3. And by his model's assumptions, the predicted correlation between 1 and 3 is just this product. So he's measuring this, he's measuring that. You don't need any econometrics. By the way, I'm the other one who doesn't know econometrics. So you don't need any econometrics. So he measures this, he measures that, and given his model's assumptions that 1 influences 3 via x2, the indirect effect of 1 and 3 is just this product. Okay? So he's basically, that's what the model's assumptions imply, where this is true, this is measured, this is measured. The fact that the product is the estimated correlation between 1 and 3, that's coming from the model. The model tells him that he should extrapolate in this way. But then the only constraint is that this has to be a correlation matrix, and correlation matrices are positive semi-definite, and this boils down to this thing. And so you maximize this subject to that. Very simple constraint maximization, and the maximal predicted correlation that you can get is 0.5. So you can get, although the real correlation is 0, the estimated correlation can go up to 1/2. And this bound is tight, and you can implement it if x2 happens to be given by this. So if x2 happens to be a deterministic function of x1 and x3, you think of x1 and x3 as objectively independent. If x2 is a deterministic function, which is essentially the normalized average of x1 and x3, then that implements this bound. Okay, so you can get from, so you can cheat with this model. You can get from 0 to 1/2. And here I basically committed to a particular model. What we're going to do in the general exercise is to have an arbitrarily given number of variables, and we're going to allow for any recursive model rather than just one particular model. Just to show you that this exercise is not purely theoretical, here's a data set. It's a real data set from the WHO, which records health-related and socioeconomic variables for all countries. So you can basically run correlations among any collection of variables that you please. Here we picked 2 variables of interest, x1 and x3. x1 is urban population in the country, the size or the ratio of the urban population in the country, and this is the incidence of liver cancer deaths. So you can see that objectively in the data, they're hardly correlated, those 2 variables. However, if you choose in our model, in that chain model with the 3 variables, if you choose x2 to be coal consumption, the estimated correlation between 1 and 3 jumps to over 0.4, which is pretty close now to the theoretical upper bound, which would be a little bit over 0.5. Now, the reason we picked this is not the largest estimated correlation you can get in the data set, but that's a one that sort of gives rise to a semi-plausible causal story that you could tell. It sounds like a at least popular media level of sophistication in terms of the causal medical mechanism. Like urban population increases coal consumption could have an effect on cancer. Now, this graph here shows you the importance of the fact that you have a pool of lots of variables you could try out. So you keep x1 and x3 fixed. Those are the variables that you care about. But then there are lots of candidates for x2. You can basically run through all the covariates in the WHO tables, and you start interviewing those candidate x2s for the job. And the job is to help you cheat with this model. And so what we did here is, what Yair did, is just order the variables, the candidate variables in some list, and then you start trying them. And at the beginning, it doesn't really help you much. And then after you try hundreds of variables, all of a sudden you manage to get a very high correlation. So this is the image that I want you to have, just a sec. This is the image that I'd like you to have, that there would be a model of a given complexity. Here in this example, the model had 3 variables, the 2 variables of interest and 1 intermediate variable, x2. But you choose this x2 from a huge pool of candidate variables. And that's why this analysis of how badly can you cheat is sort of motivated, at least in the researcher bias story, by this kind of big data environment where you can basically choose the variables in your model from a huge pool.
Can
I
he
guess
not,
this is a good point to take questions.
can he not,
Clarifying questions.
can he not choose a lot of intermediate variables instead of one? And that also is part of his strategic freedom.
That's why we're going to have a general result. So the general result will be about how badly can you cheat and with what kind of model would you want to cheat when you have any given restriction on the size of the model.
Okay.
Now, I won't talk, because of the time, I won't talk a lot about related literature. We're not familiar with that much related literature in terms of the question of how badly can you fake correlations with a misspecified model. We're not aware of the precedent for this specific question. Towards the end of the talk, I'll talk a little bit about the proof strategy, and you'll see that the proof strategy borrows concepts from the literature on Bayesian networks and directed acyclic graphs, which is something that I started doing in a few earlier papers. Then there are a few models out there, not necessarily econometrics models, but really models that try to model researcher bias. So in this sense, this paper is somehow related to that. Okay, if there are no further questions, I'll get to the model itself. Okay, so in the model, there's going to be a collection of variables, x1 through xn. Notice that the way I want you to think about that is that I'm writing it down as if the collection of variables is given, but the way I would like you to interpret that is that x1 and xn will have a fixed interpretation, like drug dosage and health outcome, whereas the other n-2 variables, essentially those are variables that you could pick from this huge pool of candidate variables. Okay, but it's not essential for the formal model to write it down like this, but this is the story that I want you to have in mind. Now then there is an objective empirical distribution P over those variables. It's not really important how we interpret that distribution. You can think of that as having a really infinitely large sample, such that you really measure a correct empirical distribution over those variables. But it's not necessary to think about this as a large sample. It could be a small sample. The marginal of P on each variable is normalized to have zero mean and unit variance without loss of generality. And then, as you'll see in a second, what's important about P is the correlation matrix. That's the data. That's the empirical regularity that is objective and the researcher cannot fudge. And that's the correlation. And so the correlation between xi and xj is denoted rho ij. We fix the correlation between 1 and n because, like I told you, I want you to think of x1 and xn as variables with fixed meaning. And so we fix the objective correlation between x1 and xn to be r. And so the only parameters in our model are n, basically is going to be the size of the model, and r, the objective correlation between 1 and n. Okay, what is a recursive model? It's a system of linear regression equations. For convenience, we are going to write it down as if there is an equation for each variable, but some equations could be degenerate. And so it's a linear regression equation. You regress xk on a handful, on some selection of other variables, but notice that those variables belong to R of k. And what is R of k? It's the set of previous variables. This is what makes the model recursive. Variables can only condition, when you write down an equation for a variable, it can only be a function of variables that already appeared on the list. Now you estimate each equation in isolation, you estimate it via OLS. So you just do OLS. Okay. So you estimate each of those equations via OLS. The point is that to get a predicted or estimated correlation between x1 and xn, you need to somehow put these equations together. And for that, you need to make an assumption. And this is where the model misspecification kicks in. The analyst basically assumes that those epsilons are, you might as well think of them as being independent. The weaker assumption is that they're uncorrelated with the other epsilons, and they're uncorrelated with the previous x's. Some of these things you get for free because of the OLS. But that's the assumption that the analyst makes. And again, to keep things easy for you, imagine that he assumes that all these epsilons are independent variables. One assumption that's looks like we're making an assumption here, which is, remember that I'm interested in the correlation between x1 and xn. And I also made x1 the first variable on the list and xn the last variable on the list. That's actually without loss of generality. We could actually be interested in the correlation between variable 4 and variable 7. So that's just a notational convenience. It's not trivial that it's not without loss of generality, but it is without loss of generality. Okay, so given those assumptions,
sorry,
how would
Rani,
yeah.
I have a small question. So I'm trying to understand what do you mean when you say so the analyst assumes that these epsilons are uncorrelated, but then so then he will choose some variables as you were describing in the example and present some data trying to convince us of some correlation. But I will assume also that the epsilons are uncorrelated when I interpret the data, or how do I think of that?
The analyst?
No, the audience.
The audience is, again, the audience is not sophisticated. The audience, you'll see that the audience will hold the analyst to a certain test, but it's a very naive test, and they're not going to test those identifying assumptions. So they're not. So basically,
I see. So he will run his misspecified model and tell me a correlation, and I'll just take that.
Again, with the qualification that there will be a certain test, but the test will not be that you assume that 1 and 3 are independent, conditional on 2. I'm not testing that. That's why you can get away with that.
Okay.
Okay, so given those assumptions,
Ronnie, sorry, just another question. So you're fixing the ordering of the n variables? Is that exogenously fixed?
Like I said, it's not important. So it's not important. But if it makes it easier for you to, again, so 1 and n is just convenient to think of x1 as the first variable and xn of the last variable. But as you'll see from our result, the other variables, it's not important because we're going to do some kind of worst case analysis. So it's not important to think of the order of the variables. So the fact that we enumerated the variables and that the order of the recursive equations is consistent with the natural enumeration, that's totally without loss of generality. The fact that we put 1 at the beginning and n at the end, it's also without loss of generality. That's just, but it's not trivial that it's not without loss of generality. So the answer to your question is that no, I don't need to think that there's a fixed order.
Okay.
But it's just not important. Okay, so you can put that aside. If it's sort of makes it harder for you to follow, don't worry about that. It's not an issue. Okay, so given the assumptions that the analyst makes, what is he going to do? How is he going to predict xn as a function of x1? He will do what you would have done. I mean, basically, you start substituting. You look at the equation for xn, and you look at the variables on the right-hand side, and you start substituting each variable with the left-hand side for that variable, except for x1. You don't touch x1. You substitute all of the other variables, and you keep doing it until you get a single equation where xn is a function of x1. It's going to look like this. There's going to be some coefficient for x1 and a bunch of some linear combination of the epsilons. The crucial thing is that this alpha and these gammas, there's some complicated, horrendous combinations of the betas. The betas were estimated from each of these equations in isolation, but now I just algebraically manipulated the system, and it's exactly what you would have done. It's a very intuitive procedure. Remember that the epsilons are treated by the analyst as effectively as independent variables. All these epsilons have 0 mean. X1 has 0 mean and unit variance. So the estimated mean of xn is also going to be 0. And these are formulas for the estimated covariance of x1 and xn, as well as the variance of xn. We just developed the right-hand side of this equation. And we make use of these assumptions of the analyst who imagines those epsilons, assumes that these epsilons are effectively independent. So lots of things cancel out, and therefore the estimated correlation of 1 and n is just this thing. And again, it's not simple because this alpha is a horrendous combination of the betas, and this thing is also kind of complicated. Now, and here's my answer to Marina's question before. The analyst will face a constraint. The audience will hold them to a certain test, to a certain standard, and the constraint is that the analyst is not allowed, the estimated model is not allowed to distort the mean and variance of individual variables. Cannot distort that. The interpretation is that, again, we're thinking about the lay audience. Individual variables are relatively easy to monitor. Some of them are payoff relevant. For example, if we have an economic model and they're estimating that inflation is very volatile, and I've been around here for 30 years, and I know that inflation has been very stable, it would be very easy for me to sort of basically reject the model for being inconsistent with reality. And frankly, another motivation for making that restriction is that whenever I try to publish papers with misspecified models and I didn't make that assumptions, the referees would complain. And there's a good reason to complain about that. And the third reason, which is the most important reason, we don't know how to prove a result without this constraint. So there are these three reasons for why we impose that constraint. We know that the constraint is binding, so it's, but we just don't have a general result without that constraint. We have a partial result without that constraint. The three variable model that I showed you in the example satisfy that constraint, so that's why I didn't talk about that. Now, let's try to see what this constraint means. Well, the linear regression equation specification means that the means are not going to be distorted. So it's just the variances. The estimated variances could, in principle, be distorted. So the constraint tells us, no, he's not allowed to distort the variances of individual variables. They have to be 1. And that means that the estimated correlation is going to be this alpha. That's the thing that the analyst tries to maximize, subject to the constraint that the variances are undistorted. So you can see that there's our problem. We think that it's interesting, even putting aside the economic motivations, we think that mathematically it's an interesting question. And we analyzed that for the case of recursive linear regression models, but it's a question that we find interesting for a larger class of models, which is how badly can a misspecified model distort pairwise correlations without screwing up the margin? And we think it's relevant for lots of economic situations. Questions before I state the main result? Okay, so the main result, which is in a sense the only result in the paper, there are a few minor results out there. I need a little piece of notation. Remember that we had two parameters in the model. R is the objective correlation between 1 and N is the number of variables in the model. So take R. You can think of this R, which is the rate of the Pearson correlation between those two variables. You can think of that as the cosine of an angle. So that's that angle that represents the correlation. Take that angle, slice it into n-1 equal parts. So you have a subangle. Let's call that subangle theta in R. So it's an angle that is parameterized by n and R. And here's the result. And you can see that we like the result. We even put a nice rectangle around that. So here's the result. Give me a generic objective correlation matrix rho. And I'll explain the genericity in a second. We think that we don't need the genericity for the result, but we don't know how to prove it without the genericity. So give me a generic correlation matrix, rho ij, with rho n equals R, because that's a parameter of the problem. If the recursive model, you have a recursive model with n variables. If the recursive model managed to satisfy the kind of the specification test, then this is the upper bound. This is an upper bound on the estimated correlation. So that's an upper bound. What is this upper bound? You take this angle, you take the cosine of this angle, and then you take it to raise it to the power of n-1. What's the interpretation of this genericity? Remember that remember this metaphor that we had of this kind of big data metaphor of this pool of variables. So I have a model with n variables. 2 of them are fixed, x1 and xn. But I can choose those n-2 other variables from a pool of thousands of variables, like in the WHO example. And then I can choose how to arrange those variables in a model. But I can choose those n-2 variables from a huge pool. Still, it's a finite pool. So with probability 1, this available pool of variables will be such that this bound holds. And maybe there's a measure 0 probability. With probability 0, we don't think so, but maybe with probability 0, the pool can generate, can be a source of variables that could relax this upper bound. Okay, so that's the interpretation of the genericity. Okay, let me say a few words about this result. Two things I want to say about this result. First, let's spend a couple of minutes with this formula and try to understand how it works. First of all, it increases with n. So the larger your model, so going back to Pradeep's question, the larger your model, the more you can cheat. So a more complicated model can cheat more. Furthermore, when n goes to infinity, the upper bound converges to 1, no matter what the true R is. The true R could be -1. Nevertheless, if you have a sufficiently large model, again, we are allowed to use, to have sufficiently many variables, you can get very close to an estimated correlation of 1, which means you can cheat very much with a complicated recursive model. Just to give you a few numbers, with R equals 0, if you don't have extra variables, you can't cheat. If you have one extra variable, that's the 1/2 that we saw in the example. And then it starts going up. You have diminishing returns, but it does converge to 1 when n goes to infinity. The other thing I want to show about this formula is that the upper bound is tight. So it's tight in the sense that I can now show you how to implement that upper bound. I need to show you the model. I mean, what would it look like? And second, what are the variables that will implement that upper bound? So the model will be simplicity itself. It's essentially the simplest model you could have, which would be if you wanted it to be connected. So it's going to be just a list of simple regressions. Xn will be regressed on x1. X2 will be x2 will be regressed on x1. X3 will be regressed on x2. X4 will be regressed on x3. So it's essentially your model can be described by a causal chain where 1 influences 2 and 2 influences 3, etc. So that's the model that gives you the upper bound. What are the variables? Well, again, you take x1 and xn. I'm sorry, that's a different way of presenting that. So each one of the variables will be, you can define that as a linear combination of two independent standard Gaussian variables, where S1 really coincides with X1. And as you move down the chain, the variable in question puts a higher weight on S2 and a lower weight on S1. And when and the reason we have these cosine and sine operations here is that what happens is that when you calculate the correlation between adjacent variables in the chain, for example, the correlation between x1 and x2, the correlation between x2 and x3, and so forth, you see that this pairwise correlation, this correlation between adjacent variables is exactly this theta n r. And therefore, the estimated correlation is just a product of those pairwise adjacent correlations. And that's why we get the cosine of this angle to the power of n minus 1. Questions before how much time do I have, Marina? Or, yeah.
You have 11 minutes until the end. I suggest you finish in 5-6 minutes.
Okay, so let me just give you a tiny kind of introduction, very tiny introduction to our approach to proving the theorem. We think it's part of the interest in the paper, not just the formula itself. So again, it's just going to be very impressionistic. So two preliminary observations. First, because the analyst projects a linear model on the data, it's as if he believes that P is a multivariate normal. It might as well be. So in this sense, rho is the only data aspect of the data that you need. You only need to know rho that fully describes P. If P is multivariate normal, then rho is sufficient to describe P. And the Kth equation is not just a linear fit. You're essentially measuring an objective conditional distribution of xk conditional on its right-hand side explanatory variable. So you really are measuring a conditional distribution. So from now on, let's keep that pretense that P really is multivariate normal such that the Kth equation really measures a certain conditional probability. That means that we can abstract a little bit from our description of the recursive model and essentially describe it by a directed acyclic graph. So R of k, remember, what is R of k? It's the set of explanatory variables in the equation for xk. Now, this function defines a directed graph where the set of nodes is 1 through n, it's just a set of variables. And you write down a directed link from j to I if j is an explanatory variable for I. So that's how you have a directed graph. And because the model is recursive, the graph doesn't have cycles. So that's why the recursive model can be defined by a directed acyclic graph. Within the class of DAGs, here is a subclass that is known in the Bayesian network literature as perfect DAGs. In a perfect DAG, there are no unmarried parents. So if there is a link from J to I and a link from K to I, then there must be a link between J and K in some direction. So that's a subclass of perfect DAG. Now, once we have those two preliminaries, we can realize that actually the model estimated joint distribution. So when you estimate the model, you essentially create an estimated joint distribution over those variables. And I use P sub R to denote this distribution. It's a distortion of the true distribution. There is a true distribution out there, but because we fit a misspecified model to that distribution, we create a distorted belief. You basically reflect the true P through the prism of this model, and the reflection is basically given by this formula. So this formula is describing the joint distribution that arises from estimating the DAG represented model. Now, it's a probability distribution to all intents and purposes. It's a distortion of the true distribution, but it's a distribution nonetheless. This formula is taken from like page 1 of any textbook on Bayesian networks. Here are a few important references. And since it's a distribution, you can use it to calculate marginals, conditionals, as well as coefficient correlation coefficients. For example, the estimated correlation between coefficient of correlation between 1 and n, that's exactly the same correlation coefficient that we saw before. It's just a different way of arriving at the same thing.
Rani, when do you want to take a question?
This is basically my last slide. Okay, so once we have this preliminaries, this is what the structure of the proof. Step 1, there are 3 steps. In the first 2 steps, we basically shrink the class of relevant DAGs. We started from all the possible DAGs. Now we start shrinking them. Step 1, if you want to satisfy the undistorted-Marginals constraint, that's this specification test that the audience imposes, then R must be perfect for almost every Gaussian P. This is how we get the genericity. So for generic P, we must settle for perfect DAG. The second step basically tells us that once we have a perfect DAG and we know that P is Gaussian, multivariate normal, then we might as well work with a chain. So it's a further reduction. The set of DAGs, perfect DAGs, now shrinks to a single DAG, which is the chain DAG. This is what this thing says, that there is no loss of generality in restricting attention to chain DAGs. Once you have a chain DAG, you can reduce the problem to an explicit semi-definite maximization programming problem, where you have an objective function that is a relatively simple, explicit formula that basically a product of correlations, of objective correlations, subject to the constraint that a certain matrix is positive semi-definite. And this is a constraint maximization problem that can be solved. It has a nice geometric interpretation where you basically represent x1 and xn in some sense as 2 points on a sphere, on an n-dimensional sphere. And when you pick those other variables, it's like you're picking n-2 other points on the sphere, and you're looking for those, and you want those n-2 points to be such that when you travel from 1 to n through those points, you travel the shortest spherical distance. And this is how we get the solution. So that's the structure of the proof. I have one last slide with open questions, but I can stop here. So thank you, I can take questions.
So Yevgeny Zalyobovsky asked the following question. So in order to obtain the upper bound, you also construct the variables under consideration. How likely would one to get close to the upper bound with more arbitrary data?
What do you mean by more arbitrary data? That's the thing I don't understand. So if the question is, suppose that you don't have, so let me try to interpret the question. If you don't have an infinite pool, but some subset, then it's a follow-up problem. We haven't done that. So we were basically looking at the worst case analysis as if the pool is unrestricted. And when the pool is restricted, it's a different problem that we don't know. We just don't know. It's not an easy problem.
Okay. Any other questions from the audience, panelists? I look and I see no raised hands. By the way,
yeah, you're right. I have a question. So, Ronnie, so you're basically precluding the idea that sort of the audience can just say, hey, show me the correlation directly between X1 and XM.
So now I'm highlighting this open question. So let me, if I have a minute, let me just go over the open questions because as a substitute for the audience's question. So question number one, let me start with this question. I have 1 minute?
4 minutes.
Yeah, so I'll have time. So one obvious question is, what about more sophisticated misspecification tests? Obviously, if you're going to run enough misspecification tests, you're going to refute any model. And so this brings us to a fascinating question for which you would need to model explicitly the reason for you working with a simple model. Because obviously, if reality is consistent with a 100 variable model, then write down that 100 variable model and it will be correct. Now, suppose that you have some motivation that I haven't modeled for using a simple model, and that model will be wrong. That's what we do in economics all the time. We work with simplified models, and we know those models are wrong. So you don't want to kill a model just because it's wrong, because every simplified model will be wrong. So there should be some kind of trade-off. You may want to introduce more specification tests, but you don't want them to be too stringent because you don't want to kill too many valuable models. So for that purpose, you need to have some kind of explicit model of the benefit of having a simple model. And you also want to have some kind of representation of the amount of sophistication of the audience. I don't want to think of the audience as being Victor Chernozukos. Okay, I want to imagine an audience which is basically like us trying to understand what all these epidemiologists are talking about in the last 6 months. But for that, you need to have some kind of modeling of the value of a wrong, simple model. And that's fascinating, and we haven't done that. Let me just go through the other open questions. One, it's a conjecture. We think that genericity is not needed. We just don't know how to prove the result without it. We have a little bit of analysis in the paper. You can find it in the paper. What happens when we relax that constraint? And there's a good reason to relax that constraint if what you're interested in is the causal inference motivation for working with a recursive model. And we have a little bit of exercise with non-Gaussian variables, but it's a tricky problem. So those are interesting questions that are, by and large, open questions.
Ronnie, thank you so much for
Thank you very much.
lecture.